The integrating factor is the go-to method for solving complicated first-order linear ordinary differential equations. And in the previous video, we saw how we can use the integrating factor for any general differential equation. But now we will apply it to a specific example. So let's say that we have dy by dx is equal to y divided by cosine of y minus x. And we want to solve not for y of x, but for x of y. So we want to solve for the set of solutions, the set of all possible functions, where x is the dependent variable and y is the independent variable that satisfy this differential equation. So now, at first glance, it might seem that this equation would be really hard to solve because we have cosine of y. Okay, and you might think that this equation, this differential equation, is non-linear. But if the set of solutions, the set of functions that solve this differential equation is x of y and not y of x, well, this differential equation can be treated as a linear differential equation. And why is that? Because x is not multiplied by itself. We don't have x squared of cosine of x. We have x by itself, and therefore it is a linear differential equation when we're trying to solve for x of y. Conversely, if we tried to solve for y of x, then we would have had a nonlinear differential equation. So now, the first thing you might try to do is use the separation of variables method, but this technique does not work in this example. So we will use the integrating factor technique. The first thing we can do is first write dy dx as 1 over dx dy. So what we do is we basically invert the differentials and do the reciprocal of that. But we can only use the reciprocal if dy dx is never equal to 0. Because if it was equal to 0, then we would have divided by 0. And therefore, we can write that 1 over dx dy is equal to y over cosine of y minus x, and therefore dx dy is equal to cosine of y minus x divided by y. And of course, we have that dx dy cannot be equal to 0 either. And now we can clearly see that we are dealing with a linear differential equation and not a nonlinear differential equation. Because here, even though we have a cosine function, the input of the cosine is y, yet the dependent variable is x. So it doesn't matter if we have a cosine of y, it stays linear. And now, to use the integrating factor, what we need to do is write it in the standard form. So what I'm going to do is multiply by y. Of course, y cannot be equal to 0. And therefore, we get that y dx dy is equal to cosine of y minus x. And therefore, we have that y dx dy is equal to, well, dx dy plus x is equal to cosine of y. And now, to have it in the standard form, we need to divide by y. We don't want to factor for the dx dy. So we get dx dy is equal plus x over y is equal to cosine of y divided by y. And so this expression over here is quite neat because it's a differential equation of the form x prime plus a of y. X is equal to b of y. Or if we want to use it in the form that we saw in the last video about the integrating factor, we have y prime plus a of x y is equal to b of x. But here we have changed the variables. Here in this differential equation, x plays the role of y and y plays the role of x. So the roles have been inverted. And finally, having this form, we can now use the integrating factor. And remember, I don't want you to memorize the formula for the integrating factor. It's way better to derive it on the spot. And you might think that it would be time consuming to derive the formula for the integrating factor on the spot. But actually, it can take just a few seconds. So let me show you why. So the method consists of multiplying by a factor, a function, r. So r of y in this case, x prime plus r of y times 1 over y is equal to r of y cosine of y divided by y. But now we want r prime of y to be equal to r of y divided by y in order to get the derivative of a product. So we want r prime of y to be equal to r of y times 1 over y, which means that r prime of y divided by y is equal to 1 over y. And so we integrate on both sides to get that ln of r of y. Remember, r of y is a positive function. You can check out my previous video on the integrating factor to understand why. Is equal to ln of y. And hence, we get that r of y is equal to y. And therefore, y is our integrating factor. And so, we get that d by dy of the product of y times x is equal to cosine of y divided by y. But remember that we multiply by the integrating factor, so the y cancels out. So we just have cosine of y. And therefore, if we integrate on both sides, we get that y of x, y times x is equal to the integral, well, the antiderivative of cosine of y is sine of y. But we can't forget about the constant here. And hence we get that x, remember we're trying to solve for x as a function of y, is equal to sine of y divided by y plus c over y. And there we have it. This represents the set of solutions that satisfy this differential equation over here. In the case where x is the dependent variable and y is the independent variable. So remember that even though at first sight this differential equation seemed complicated because we have a cosine of y and we would think that we're dealing with nonlinear differential equations. Actually, since the set of solutions involves trying to find the function x, well, we realize that our differential equation is actually linear, and therefore we can use the integrating factor. And there we have it. Thank you for watching this video.